So what we're talking about today is section 5.5, implicit differentiation. So I'm taking derivatives of functions that I can't see. almost like they're invisible. They're not quite invisible, right? Like I bought a dictionary the other day, and I had to return it because I said, look, the word right here is invisible. I can't see it, right? Another word in there was misspelled. I'm like, I can't believe you have a misspelled word in a dictionary and you're going to try and sell it to somebody. It's a joke. Okay, so explicit is something like we're used to. All of my x's are on one side, right? And implicit is going to be they're commingling. So notice that this is equivalent to what? xy equals 1, right? So this one is explicit, and this one is implicit. So we're going to look at how I can solve something explicitly, which we know how to do already, right? And then how we can solve something implicitly. Now this one, I don't have to do it implicitly, right? Because I already know how to do this derivative, right? My phone just told me to go to work. So, but sometimes we won't be able to solve for x. And that's when we are forced to do something implicitly. Okay? So on the left side, it's almost instant, right? This is our shortcut. This is a power rule. Does anybody have it memorized? Very good. 1 over negative 1 over x squared. This is our shortcut, right? Do you want to see the power rule on this one? Yes. So I know that this is x to the minus 1. So for my power rule, I'm going to bring down the negative 1, bring down the power, reduce the power by 1, right? So I get negative 1 over x to the, negative 1 times x to the minus 2. So there it is. There's my explicit. Implicit, notice what I'm going to have to do. What do I have on the left-hand side here? A product. So the first function is x. I know how to differentiate in terms of x. This is what? Derivative. 1. The second function is g is y. And whenever I've taken a derivative of y, what do I get? Y prime. So g prime is y prime. That's how easy it is. I have to always think of the chain rule, right? The outside function is the inside function, right? In this case. So what do I get from my product rule? I get y prime is xy prime plus y. Oh, sorry. I got to differentiate both sides, right? So look at what I'm doing, sorry. I'm doing ddx of both sides. So on the right-hand side, ddx of 1 is 0, right? Differentiating both sides. Just like I did on the left. Look, did I differentiate the left side? Yes, I got y prime. Did I differentiate the right side? Yes, I used my shortcut, right? So I'm doing the derivative of the left side with a loop, product loop. Derivative of 1 on the right side is 0. What am I solving for? What did I solve for? The derivative. I'm solving for y prime. So xy prime equals negative y. So y prime is negative y over x. Do I know what y was? Did I have an original y equal anywhere? Yeah. So negative 1 over x. So there it is, negative 1 over x squared. Same answer. So I want to think about things. If I'm differentiating something in terms of x, I know my rules. If I'm differentiating something in terms of y, I have to think of y primes. I always now must think of the chain rule, okay? All right, so here we go. Just a couple of quick examples. Yes? A couple of quick examples. If I'm doing d dx, that's my operator of 2x, right? What do I get? 2. If I'm doing d dx is my operator that says take a derivative with respect to x, right? Of sine of x. What do I get? Cosine of x. If I do d dx of y squared, what do I get? 2y is the derivative of the, remember, the outside function is something squared. So 2 times that something, now derivative of the inside, y prime. d dx of the square root of y. Outside function is the square root function. I know the derivative of that. It's 1 over 2 square roots, but I want to keep what was inside. So, and then I need to do the derivative of the inside, y prime. d dx, oops, I keep doing that. d dx of tangent of x plus y. This is one of my favorite problems. Tangent of, that's a tangent, believe it or not. Let me try again. Tangent of x plus y. Outside function is tangent. We know the derivative of tangent is secant squared. So I get a secant squared, but I want to keep the cat in the box. And then I want to multiply by x plus y prime, right? So this one, because I'm a little concerned about rushing, I want to put that placeholder in and remind myself I've got to take the derivative of the inside. So what do I get? I get secant squared of x plus y, that's one function, times derivative of x is 1, derivative of y is y prime. It's so easy. Implicit is easy. It's very, very easy. When I write y prime, okay, which is Newton's notation, I'm always assuming I have differentiated in terms of x. When I write dy dx, which is Leibniz notation, right? He was a German guy. Newton's English, this Leibniz German, they supposedly both discovered calculus at the same time, but they had different notations. I will use dy dt. Whenever I'm differentiating with some other variable, I'll always write it as Leibniz notation. dy dt tells me I have y prime, but in terms of the variable t. Sorry, yes, time, in terms of time. Does that make sense? So I don't like writing dy dx. I like writing y prime. It's a lot quicker. But in this case, I won't write y prime because the variable that I'm differentiating with, it gets lost. When I'm differentiating with time, I'm going to use d dt. When I'm differentiating with x, I'm going to use y prime. Okay? So I'll remind you when we get to that in chapter 4. Okay? All right, let's look at a couple of interesting problems. Almost done today. It's that easy. This section is this easy. It really is. So we're looking at implicit differentiation, and they're pretty complicated right away. Let's do one that I like with a graph. Let me find it. I'm sorry. Here it is, number 23. Now, this one, I cannot, well, I'll be careful there. It's hard to solve this for y, okay? But it turns out that it's an ellipse. And on all problems like this, I'm going to give you a graph on the test. So if you go look at my old midterms, you'll see a bunch of graphs on there. They're usually the implicit problems. Because since you can't solve this for y, you can't graph it on you can't put it in your calculator. So it's unfair for me to expect you to be able to visualize this. So I'll give you the graph, okay? So I'm looking at 3.5, number 23. And I've got x squared plus xy plus y squared equals 3. And I want to find a tangent at 1, 1. So I want to find the tangent at 1, 1. So first of all, let's take a look at this graph, okay? So I've got x squared plus xy plus y squared equals 3. And I'm graphing, I want the tangent line at 1, 1. There it is. Well, I can kind of see it, right? I can kind of see the line. Definitely has a slope of what? -1, and it looks like it might hit at 2 for the b value, right? Let's just guess. Y minus x plus 2. Oh, y equals, sorry. Yeah, that's it. So, but we want to do what? Well, we got a point, we need a slope, right? So we need a slope. Now, a lot of times on this, I'll say find me the slope implicitly. It means I don't really need to see a nice version of y prime, okay? In this case, I can get a nice version. Sometimes I cannot, okay? So just look at the directions. If it just says find a slope, put the numbers in. If it says find the derivative, then you want to solve for y prime, okay? Let's see if we can do both. So let's find y prime here. I want to do d dx of the left side, and that should equal the derivative of the right side. Derivative of the left should equal derivative of the right. So on the left, I got the first piece right away, right? It's 2x, yes? Then I need an xy prime, right? I'm going to wait on that. But the last one I can do right away, 2y prime. Do we agree there? Right, so derivative of x squared is 2x. Derivative of y squared is 2y prime, right? Did I do the chain rule on both of those? What's the outside function here? Y squared, it's a square. So I have to do the derivative of the inside, which will give me a y prime. Did I do the chain rule here? Yes. You always do the chain rule. So the derivative of x squared is 2x, and the derivative of the inside is 1. Always, always, always do the chain rule. So the piece I have left over, I'm going to do with a quick loop, right? First function is x. Oh, can you see the green? Probably not, right? First function is x, derivative is 1. Second function is y, derivative is y prime. So now I get 2x plus xy prime plus y plus 2yy prime equals 0. Make sure you see that everything I got from my loop, right, is here. Yes? Yes.
I have a question.
Yes. Go ahead, Ivan. One more time. Derivative of x squared. Yep. Go ahead, Claire.
Yeah, so if you, just hypothetically, if you were to write d dx as dy dx, could you assume that the y was a constant and then the derivative would be 1?
Yeah. I mean, you're talking. You're talking about just using the ddx notation.
Well, yeah, like if we use the other notation, then like would.
It's not wrong. It's not wrong. So it would look like this, though. It would look like x times dy dx plus y plus 2y dy dx. And you can see why I like using just the y prime. It's just quicker. Yeah, I'm lazy. So I want to get a nice version of the derivative. So I need to solve for y prime. So I'm going to rewrite, right, keeping my y prime terms on the left and move my other terms to the right. So negative 2x minus y. Agreed? The 2x has no y prime in it. I move it to the right. It becomes the opposite. The y has no y prime factor in it. I move it to the right. It becomes opposite. Now I can factor out my y prime. And then divide to solve for y prime. I certainly can factor out a negative right? And there's a nice version of my slope, of my derivative. So what slope do I get when I plug in 1 for x and 1 for y? So m equals y prime at 1, 1, right? So negative 2 times 1 plus 1 over 1 plus 2 times 1. So negative 3 over 3, negative 1, right? Tangent line, yes. So y minus 1 equals negative 1 times x minus 1. Remember, my point was 1, 1. So y minus 1 is negative x plus 1. Y equals negative x plus 2. And that's what we graphed already. I think that section is fun. I think it's pretty easy.